In section 9.3, we're going to use the ideal gas law to compute gas densities and molar masses. We'll perform stoichiometric calculations involving gaseous substances, and we're going to state Dalton's law of partial pressures and use it in calculations involving gaseous mixtures. So we're going to recall that our molecular weight is the mass of something divided by its how many moles there is of it. And rearranging that, for moles, we can see that the moles of something is the mass of it divided by its molecular weight. If we substitute in the mass divided by the molecular weight for N into our ideal gas equation, we get this equation now, where PV equals the mass times R times the temperature divided by the molecular weight. If we choose to look at this as the mass divided by the volume times RT over the molecular weight, we get this M over V term. And if we recall, that is the density, the mass divided by the volume. Substituting in that density, we get this equation. And then rearranging and solving for the density, we can see that the density of a gas is the pressure times its molecular weight divided by RT. So density is an intensive property. We're going to remember that. That means it does not depend on the size of the system. But the density of an ideal gas does depend on the pressure, temperature, and molar mass. We can also solve that equation for the molecular weight, and we can see that the molecular weight is equal to the density times the ideal gas law times the temperature divided by pressure. Or we can substitute in our value for density here. If we have the mass and volume, we can see that that is MRT divided by PV. We can measure the mass of a gas pretty simply doing some experimentation. We can measure a flask that is sealed at the top, inject that gas into it. It is typically then condensed, so we cool it way down until it condenses into a liquid at the bottom, and then we reweigh that flask. Dalton's law. So the ideal gas law also applies to mixtures of gases if the gases don't react with one another. And this leads us to Dalton's law of partial pressure, which is that the total pressure of the system is going to be equal to the pressure of each one of its components. So if you have A in a flask and it has a pressure, B in a flask and it has a pressure, you add them all up to get the total pressure. The pressure exerted by each individual gas in a mixture is called its partial pressure. The partial pressure is equal to the pressure that the gas would exert if it was all by itself. And we can picture that here. If we had 3 containers, each with a different gas in it at a different pressure, when we combine them, if we combine them all together somehow into a different tank, its pressure is going to be the summation of all those pressures. So now I want to introduce the mole fraction. This is a type of concentration. It is expressed as the fraction of moles of a particular component in a mixture to the total moles of all components. So if a mixture contains A, B, and C, the mole fraction, this is a capital chi, a Greek letter, of A is going to be the number of moles of A over the total moles of A, which would be the summation of A, B, and C. Similarly, we could have the mole fraction of B and the mole fraction of C. If we know all of the mole fractions of all of the components, then they will sum together to equal 1. And we can see that expressed here using sigma notation. When only the total number of moles is known for the mole fraction, it can still be expressed as the moles of any particular component over the total number of moles. this can be rearranged to yield that the total number of moles of A is equal to its mole fraction times the total number of moles, which is how this operates as like a concentration unit. So let's extend this logic to Dalton's law now. We can express the partial pressure of a gas in a mixture in terms of its mole fraction. So we can say that the pressure of A is equal to the mole fraction of A times the total pressure in the system. And we could do the same thing for B. If we then have Dalton's law and we make these substitutions in, we can see that the total pressure is equal to the mole fraction of A times the total pressure plus the mole fraction of B times the total pressure, so on and so forth. So a common way to collect a gas is to collect and quantify it by capturing it over water. This can be done pretty easily and pretty effectively, and it's the way that they've been doing it for a long time. But it does come with a caveat in that that gas is going to pick up some of the water that it's bubbled through. So if we imagine a gas is escaping here and it's being trapped up in here, it's going to pick up some of that water vapor. And in doing that, we're going to have to make a correction. So we refer to the gases collected over water as wet gas mixture. The pressure of these gases must be corrected to account for the water they contain. Say, for example, that the gas being collected was H2. The total pressure that we're measuring is going to equal the pressure of the water that's in the gas plus the pressure of the H2. We know from Dalton's law that these would sum together to give us the total pressure. And we have a special name for the pressure of the water. It's known as the vapor pressure of water. The pressure exerted by water vapor in equilibrium with water in a closed container is the vapor pressure of water. This is an intensive property that does not depend on the amount of water, but it does depend on the temperature. So basically, we know what the vapor pressure of water is at any specific temperature. So we just have to go and look up for our temperature of our experiment what that vapor pressure is in order to get that term and make the correction. Stoichiometry and gaseous reactions. Gases may appear as reactants or products in a chemical reaction. The ideal gas law and a balanced chemical equation can be used to relate the pressure, volume, temperature, number of moles, and grams of a gas that takes part in a chemical reaction. Stoichiometric factors can be used to relate the moles of one substance to the moles of any other substance in a balanced chemical equation. So we were figuring out moles before, and now we have an equation to relate the moles to the pressure, volume, and temperature. So this allows us to do some different, a little bit more complex calculations. So one thing to look at is the volume ratio. The volume ratio of any two gases in a reaction at constant temperature and pressure is the same as the stoichiometric ratio, mole ratio, in the balanced chemical equation. So that means that the volume of gas A over the volume of gas B is going to equal this. We saw that earlier when we were deriving the ideal gas law. If we cancel those K values, we can see that this is equivalent to the number of moles of A over the number of moles of B. Here we can picture how stoichiometry can work out. As we see here, before when we were looking at different molecules, we could just picture those as groups of atoms that were contained in little systems that move along. And this also, interesting at the end of this chapter, is a little talk about climate change. So now with everything that we've learned, we can talk about this a little bit. We are on the Earth, and we are surrounded by all of these gases. And the sun shines down its radiation on us. And this is high energy radiation, right? This is high electromagnetic radiation. So some of it bounces off, but most of it actually has enough energy to go all the way through. After it hits the Earth, it excites some electrons, and then it's going to emit radiation that's of lower energy. This is mostly in the form of infrared radiation, and that doesn't have enough energy to exit the Earth when we have a thicker layer of gases on the outside. And that's what causes the Earth to eventually heat up. It can't get rid of the infrared radiation that it's emitting fast enough to maintain its temperature. The rise in carbon dioxide levels are pretty undisputable at this point. And we'll give a little shout out to Susan Solomon for her research in doing in climate change. And there's a nice little blurb about her in the book.